3,200 kilometers is almost the length of the massive border wall. This equals the distance from the Pacific Ocean in California to the Atlantic coast in North Carolina. Donald Trump pushed this project after surprising the world as president. But this is just the beginning. Why is this structure considered such a complex engineering feat? The harsh environment presents obvious difficulties. However, the true challenge lies in building a huge steel barrier capable of withstanding these conditions. One can notice tall steel posts nearly 30 feet high, rising vertically. At first glance, the construction seems simple, but in reality, the columns are set deep in concrete for maximum stability. The camera glides along the metal line, revealing an almost unbreakable barrier. The wall thus stands firm on the southern border. 851,000 illegal crossing attempts were recorded by U.S. Customs and Border Protection in 2019 alone. Why was the border like a door left slightly open for decades? It seems simple to secure a boundary line. To deal with the problem, the U.S. government started building the first fences in the 1990s under President Bill Clinton. One can notice how George W. Bush and Barack Obama continued to expand the system later. At first glance, the fences seemed solid, but in reality, they were only a few meters high. It is visible that they were fairly easy to climb or cut through. But this is just the beginning. By 2016, Donald Trump turned the idea of the wall into a major part of his political message. The approach to security shifted noticeably. 1,930 miles is the vast distance the planned barrier covers along the border. Why did the Department of Homeland Security reject the initial proposal for a solid concrete wall? It would seem that a solid structure offers the most impenetrable defense. But the agency argued it would stop patrol agents from seeing what was happening on the other side. Consequently, the final design utilized tall steel posts known as bollards, which remain strong, high, and see-through. One can notice that this design became the main model for the border wall we see today. Engineers initiated the construction process by meticulously surveying the land. The route crosses many different types of terrain, from soft, sandy desert that can sink under weight to wet clay areas near the Rio Grande River. But this is just the beginning. In contrast, hard rocky mountains in Arizona and California feel like natural concrete. At first glance, the ground looks consistent, but in reality, teams had to measure elevation and drill soil samples to check how stable the ground was. They calculated exactly how deep the foundation needed to be in each location. Because this survey step was critical, it determined the entire foundation design and the structure of the wall that followed. 30 feet. Exactly the height required for the steel posts to loom over the desert landscape. This vertical scale demands an uncompromising base, as the foundation determines the structural destiny of the entire wall. Crews initiate the process by digging a continuous trench ranging from 24 to 32 inches in width. The excavation descends between 6 and 10 feet into the earth to secure the structure against potential damage. At first glance, digging a hole seems simple, but in reality, this phase proves to be one of the most time-consuming and labor-intensive parts of the entire project. Excavators and bulldozers cut through soft sand with relative ease in specific sectors. Why do engineers bring in hydraulic rock breakers for the majority of the route? Standard digging machines become useless against the granite and sedimentary rock sitting right under the surface. Without high-impact force, the ground would remain impenetrable. Therefore, heavy excavators equipped with hydraulic hammers strike the ground non-stop, cracking the rock to remove large, stubborn chunks. One can notice how the specialized trencher moves in to refine the rough cut. These high-power machines operate on diesel engines generating between 250 and 400 horsepower. This output allows the mechanism to cut through hard ground at a steady speed, straightening the walls and deepening the channel. Simultaneously, the equipment crushes any remaining soil and rock to leave the bottom perfectly flat. A conveyor system at the back constantly carries loose material out of the trench like a mechanical stream. Consequently, the machine handles hundreds of meters of trench per day, greatly speeding up the construction workflow. But this is just the beginning of the structural reinforcement. Construction crews begin installing a reinforcing steel frame composed of vertical bars and horizontal ties. This forms a continuous steel cage running along the length of the excavated path. A reinforced concrete layer between 4 and 8 inches thick is poured immediately over the set rebar. The mixture flows around the metal, creating a flat and stable base that prevents the panels from sinking or tilting. When the concrete bonds tightly with the cage, it creates a solid foundation block capable of resisting pulling forces and twisting. This anchors the wall against the intense pressure of desert winds. The structure is now prepared for the next phase of assembly. 26 feet of vertical steel define the dimensions of every bollard post arriving at the construction sector. After the foundation is ready, the site moves to preparing these main wall parts. The posts are hollow tubes, either round or square, with a thickness of 10 millimeters. Why choose hollow tubes instead of solid bars? At first glance, solid steel seems stronger, but the hollow design reduces weight for transport and allows concrete filling later to reinforce strength. Due to the massive size, each post weighs between 250 and 400 kilograms. Heavy-duty trucks deliver the elements from the factory. One can notice the posts stacked in layers and secured with steel straps. This prevents shifting during the trip. One can observe mobile cranes lifting each bundle off the vehicle. Operators place the load in a storage area, avoiding impacts that could damage the steel. But this is just the beginning. Outside the work zone, a temporary fabrication area uses welding machines to connect posts into panels. Typically, 4 to 6 posts form a single section depending on the width. Welding sections makes installation faster than placing single posts. It looks outwardly simple, but in reality, it requires geometric consistency. It is visible how a crane lifts the entire panel to place it directly into the trench. Therefore, the margin for error is non-existent. A mistake of a few millimeters at the welds causes the panel to lean. This makes alignment and anchoring difficult. The panel settles, completing this phase. 1,130 miles, precisely the distance across which the barrier must maintain structural integrity. Once the steel panels are welded together and transported to the excavated trench, the construction site enters the phase many engineers consider the backbone of the entire project. Setting the wall panels, aligning them with absolute precision, and pouring concrete to lock them in place determines how straight, strong, and long-lasting the structure will ultimately remain. Why is the lifting process considered one of the most volatile stages? It might seem that the cranes simply need to hoist the weight, but because each panel stands almost 9 meters, or about 30 feet, tall and long, the metal sheet acts like a giant sail against the elements. Large mobile cranes or truck-mounted units slowly lift each panel, which can weigh hundreds of kilograms, off the ground. Even a strong gust of wind can make the suspended steel sway dangerously during the ascent. That is why 2 to 3 workers on the ground always hold guide ropes, working closely with the crane operator to position the panel correctly over the open trench. One can notice the steel settling into the earth, but this is just the beginning. At first glance, lowering the panel seems like the final step, but in reality, engineers are only beginning the most critical task of alignment. They use laser levels, spirit levels, and tension guidelines alongside their own experience to make sure each panel stands perfectly vertical. Even a small tilt of a few degrees can cause gaps, bending, or a crooked wall, which would weaken the structure and ruin its appearance. The process is only gaining momentum. It is visible how workers temporarily weld the base of the panel to steel anchors or support frames already placed in the trench. These welds hold the heavy panel steady while it waits for the concrete pour, preventing it from tipping over due to wind or accidental impacts. The steel now stands rigid, ready for the final solidification. Thousands of pounds of pressure from wind gusts or accidental impacts are the first enemy of the newly installed panels. Why is the concrete poured immediately after alignment? The heavy steel structures stand vertically in the trench, vulnerable to shifting. Without this rapid fixation, even a slight deviation would compromise the entire defensive line. But this is just the beginning. A concrete mixer truck or a heavy-duty pump moves precisely to the very edge of the open trench. Fresh mixture flows directly around the base, filling every void between the steel and the excavated soil. Workers immediately use tamping rods or mechanical vibrating tools to eliminate air bubbles. This ensures the concrete presses tightly against the steel surface to form a solid bond. At first glance, the hardening mass looks like simple filler, but in reality, it acts as a hidden anchor locking the bottom firmly into the ground. This drastically increases resistance to pulling forces and vibration. It gets more complex further on. In critical zones, such as near roads or soft ground, crews add an extra reinforcement layer extending about 5 feet outward from the wall. One can notice how this creates a wide foundation pad that helps spread the weight and prevents the soil from eroding or sinking over time. And this is not the limit. This wider concrete base makes it much harder for anyone to dig under the wall. Instead of going through loose soil, an intruder trying to cross would first have to break through a thick layer of concrete before reaching the steel posts, making the job extremely difficult and time-consuming. The foundation creates a secure baseline for the structure. High-pressure water jets blast the steel surface with relentless force immediately after the panels are secured. The installation itself is extremely difficult and time-consuming. However, workers must immediately deploy hoses to scour the entire surface area. But this is just the beginning. Why is such intense washing required before coating? Ideally, the steel would be clean. This step removes dirt, sand, mud, and oil that accumulate during the process. One can notice how the stream dislodges stubborn welding slag and metal fragments left over from the joining. Such debris must be completely eliminated from the segments, because if these materials stay, the paint will not stick properly. The high-pressure water is sprayed strictly from top to bottom along each panel to ensure no residue is left behind. It gets more complex further on. Workers carefully follow the direction of the panels to guide the flow. This prevents water and debris from building up in corners or gaps. At first glance, this seems like a simple cleaning routine, but in reality, it determines the wall's longevity. Thanks to this, the anti-rust coating and protective paint can stick evenly and firmly. This improves durability and corrosion resistance, which is extremely important in the harsh desert environment. The metal is now ready for the next stage. One final layer of protection transforms the vertical structure from a simple obstacle into an impassable fortification. Why is the installation of razor wire strictly prohibited for civilian workers? At first glance, it seems like a standard construction task suitable for general contractors. But in reality, the extreme sharpness of the coiled blades and high security requirements mandate that only military or border patrol units handle this operation. Razor wire possesses edges as sharp as actual razor blades, designed specifically to inflict deep cuts upon even the slightest contact. One can notice how the heavy coils are carefully lifted into position, either by specialized hydraulic equipment or manually depending on the specific location. This process requires absolute precision to avoid injury. But this is just the beginning of the securing phase. Soldiers proceed to rigidly fix the wire using heavy-duty metal brackets and steel anchor hooks. Every connection is tightened to ensure the coil remains immobile and cannot be pulled aside or shifted by external force. This manual reinforcement makes the top of the barrier nearly impossible to scale with bare hands, significantly increasing the wall's defensive capability. The perimeter is now fully fortified, ready to perform its function without further intervention. 15 billion United States dollars is the sum consumed by the total cost of the wall and its related infrastructure. This massive figure covers raw materials, transportation logistics, surveillance technology, and labor costs. Hundreds of new miles of fencing now stand complete, reducing the number of easy crossing points to allow agents effective control. One can notice how the steel barrier stretches across the horizon, physically reinforcing the border. But this is just the beginning. Why does the budget estimate continue to grow relentlessly? The structure requires constant attention to remain functional. Maintenance and repairs cost hundreds of millions of dollars every year. At first glance, the wall slows down illegal crossings, but in reality, cartels have found ways to get around it. However, the environmental price rivals the economic one. Construction raises concerns for the desert ecosystem and the Rio Grande River region. It is visible how the fence affects natural water flow during seasonal rains. Many experts argue that the infrastructure disrupts the ecological balance by blocking wildlife movement. The process is only gaining momentum. While the border wall provides benefits, it remains far from a perfect barrier, and the struggle continues. 45 feet, exactly the height reached by the massive concrete walls guarding the Japanese coast. While America constructed a barrier to keep people out, Japan faced a much more powerful enemy in the form of devastating tsunamis. Why pour over 12 billion United States dollars into static fortifications? It would seem simpler to just relocate towns further inland or build smaller levees. But these towering walls are designed to buy precious minutes for evacuation when waves rise higher than buildings. A lesson learned after the great loss of the 2011 disaster. 250 miles of defenses stretch along the shoreline, with foundations plunging 80 feet deep into the earth. But this is just the beginning. Crews begin by clearing the entire designated route of old houses, power lines, pipelines, and damaged infrastructure. Because the Tohoku coastline took the full force of the catastrophe, the defense line covers nearly 400 kilometers. It extends continuously through the prefectures of Aomori, Iwate, Miyagi, and Fukushima to form a unified shield. One can notice how engineers simultaneously build access roads, material yards, crane platforms, and concrete mixing stations to support the logistics. At first glance, the sandy soil of the coast seems solid enough to build on, but in reality, it is too weak to support a wall of this magnitude without sinking. Therefore, builders first drilled detailed surveys and installed deep steel or concrete piles to reinforce the ground. They add layers of crushed stone and compacted sand to stabilize the surface against sliding. This creates a solid base that will not crack over time, even during the rainy season when temporary drainage systems keep the site dry. It gets more complex further on. Excavators dig massive foundation pits more than 20 meters deep into the stabilized earth. Near the shoreline, workers construct temporary cofferdams or retaining walls to hold back the seawater during the pour. A base layer of concrete covers the bottom, followed by dense steel reinforcement cages. It is visible how the heavy foundation blocks form a wide foot to prevent the wall from tipping over under the impact of powerful waves. Consequently, the main structure rises from this anchor using optimized lab designs. Formwork is set in place, and pumps fill the molds with concrete section by section to ensure structural integrity. Each block, spanning several dozen meters, is cured, inspected, and connected to the next to form a continuous barrier. On the ocean-facing side, the equipment gradually stacks tetrapods and delis. These special concrete units break the force of the waves before they hit the wall. And this is not the limit. Some sections utilize stepped faces and splash reduction ledges to drastically lower water surges. On the landward side, trucks dump soil and crushed rock to create drainage channels that prevent rainwater from pooling behind the wall. Many stretches feature inspection roads or even public roadways integrated directly onto the top of the barrier. Railings, fences, and safety ladders act as essential access points for maintenance crews and the public. One can notice how cranes lift interlocking precast concrete blocks to reinforce specific sections against erosion. These panels are arranged in a tight, uniform pattern to create an armor layer that protects the structure from the constant pounding of the Pacific Ocean. The unified defense line stands ready to withstand decades of relentless saltwater exposure. Thus, the coast secures a shield capable of resisting the ocean's fury without yielding. Decades of pounding from the Pacific Ocean crash against the reinforced concrete. Two of the largest walls ever built now stand complete. Why build at such a scale? The cost is immense, but protection demands it. The massive United States border wall and Japan's towering tsunami barriers represent humanity's determination to protect itself against the greatest threats we face. At first glance, they stand still, but in reality, the defense is active. One can notice the unyielding stance of the structures. These engineering feats remain as silent guardians,